At the beginning of class today, you should have received a worksheet called the area so far function. Hopefully that worksheet makes sense. Basically, I gave you 3 different functions, and you are finding the area under the curve starting at 0 up to a specific point that they gave you. So that very first function, I believe it was f of x was equal to 3. So you found the area from 0 to 0, which is 0. Then you found the area from 0 to 1, 0 to 2, 0 to 3, so on and so forth. If that didn't make sense until just this moment in time, go back and finish that worksheet. Redo it if you need to, and then come back to this video. Otherwise, this whole video won't make any sense to you. But if you did understand it, basically what you should have recognized is that if my original function, if it was f of x, was equal to 3, when you found the area under the curve, that turned into 3x, okay? This is what we call the antiderivative. Antiderivative. Because if I take the derivative of 3x, what is that? You get 3. So that means the area under the curve of 3x is the antiderivative of what I currently had. So to label that as antiderivative, we say capital F of x, and I'm going to put plus c, because you're like, wait, why? Just know that it's there, and it'll make sense as we go on today, okay? So basically, here's what's happening. We have equations that are called differential equations. They are equations that involve x, y, and your derivatives of y, okay? They look like this. All right, y prime is equal to 3x, y prime is equal to x squared plus 1, or x plus y prime equals y minus x squared. We've seen this kind of stuff before back when we did implicit differentiation, okay? So all of the solutions to any of these equations are called general solutions because they will generally work, okay? Yet again, you're like, Murphin, what? Okay, just know that this is a thing. So we have differential equations, we have antiderivatives, we have general solutions. Let's see if we can somehow tie all of these things together. Okay, so let's say that I told you that I took the derivative of something and I got x as a result. What could that something have been? Well, what do you think? That something could have been x squared over 2. Because if I take the derivative of x squared over 2, oh, well, that's equal to x, right? So then the antiderivative of this would be this, would be that x squared over 2. Huh, curious, interesting. Well, what about the antiderivative, or what the derivative of something is x cubed? Question is, what is that something? Well, the something would need to be something to the 4th power that reduces, so x to the 4 over 4. This is one possible answer, that if I took the derivative of this, I get x cubed, okay? You're thinking like, wait, that's the only possible answer. What are you talking about? Well, what if I did the derivative of x to the 4th over 4 plus 2? Well, that's also equal to x cubed. Okay. So because I have 2 possibilities here, when we want to say our general solution, that's where we say f of x plus c, okay? Because this f of x comes from this guy right here, plus c represents all of the possible constants we could have. I have no idea, but anytime I take the derivative of a constant, I end up with 0, so I still need to account for that in some way. So then basically we have what is called the backwards power rule. If I were to take the area under the curve of some function written in the form of x to the n with respect to x, okay? Remember how when we took the derivative, we would have the derivative of blah with respect to x? Now this right here just means we're integrating our function with respect to x. Whenever you get into multivariable calculus, which is essentially Cal 3, when you get to college, some of you will get there, some of you won't, that's fine. But basically, you're going to learn how to integrate with respect to other variables. We have differentiated with respect to other variables in this class. Remember when we did implicit differentiation, when we differentiated with respect to time, with respect to x whenever we had y. I mean, we did all kinds of stuff. Remember we had like dy dx and all that good things. So basically we only differentiate with respect to other variables in our class. later on down the road, you can integrate with respect to other variables. We just don't do that in Cal 1 and Cal 2, but you will see that in Cal 3. Okay, so anyway, back to the point. So integral of x to the n dx with respect to x is now going to be x to the n plus 1 over n plus 1 plus that undetermined constant c. Okay, we have to have more information to figure out exactly what c is, which sometimes we will, sometimes we won't. So whenever we take the derivative, sorry, the antiderivative of basic polynomial functions, like written in the form of x to the n, this is the pattern of how we would get our antiderivative. Okay, so let's keep going here. Well, okay, so we've already talked about this unknown c, all right? So let's talk about how we would solve this differential equation. So let's say I wrote it as dy dx is equal to f of x. What on earth? I want to know what is y, okay? When we're solving this differential equation, basically we are solving for y, because y is going to be some function that satisfies this equation. So I need to isolate that guy right here, okay? So the first thing I need to do is get rid of the dx. So I can multiply both sides by dx. What? You had no idea you could do that? Hey guys, you can multiply by dx. So now I have dy is equal to f of x dx. Well, to get rid of, so both of these represent derivatives or differentials here. Okay, there's a whole section in your textbook about differentials. It's highly intriguing. It's just not something that we necessarily have to go over, so I usually don't. But if you would like to read into that, you are more than welcome to. Knock yourself out. But basically, to undo a derivative, we have to integrate. But when we integrate, it has to be in terms of all one variable, because that's all we know how to do in our class. Okay, so I can't integrate from here because I have too many variables on this side. So before I can integrate, I need to move the dx to the other side. It cancels there, so that way I just have the integral of dy and then f of x dx on the other side. Well, the antiderivative of dy is the function y, which is what we're looking for. The antiderivative of lowercase f of x with respect to x, we call that capital f of x plus c. So the antiderivative plus c. This is what we call our general solution. Okay, visually on the graph, this is what's happening. Okay, well, I think I have a graph of this. Let me see. Okay, so we have different parts of this. Okay, so inside the integral, we have what is called the integrand. Okay, move this over. All right, out here, oh, not out there. This is my variable of integration. So just like we differentiated with respect to x, now we integrate with respect to x. Okay, on that last bit right here, we technically integrated this side with respect to y. It works the exact same way as you would with respect to x. Okay, and then over here, actually let's go here. That is our antiderivative of f of x, and then that plus c is our constant of integration. So that's breaking down all of the parts. And then graphically, as promised, what on earth? Okay, so let's say we had the function, well, we had some function, and its antiderivative was x cubed minus x plus c. This plus c right here, I have no idea what it is. But thinking back to transformations of functions, a plus c on a function is basically just going to slide your function up and down. It's a vertical translation. If c is -4, it's going to bring your function down 4 units. If c is +1, it's going to bring it up a unit. So all of these are the possible values of c. So c equals -4, -3, negative, all the way up and down. Okay? I can't solve for c unless I have something called an initial condition. In this case, the initial condition they worked with was 2, 4, which means if I plug in 2 into my function here, then I should get 4 as my y value. So I could plug in a 2 and then solve for c, and that gives me the correct value of c here. Okay, I know that's a little bit tricky. I'm going to show you an example of that here in just one second. Okay, but again, this whole thing right here, we call this our general solution. Okay, so let's practice this a little bit. So if I have just the antiderivative of x with respect to x, okay, my function is x. The antiderivative of x, using that reverse power rule, is just x to the n plus 1. Well, this is x to the first, so 1 plus 1 is 2, and divided by 2 plus c. It's the antiderivative. We learned how to do the derivative going forward with the power rule. Now we're just going backwards. Everything we're doing is going in the exact opposite direction of what we did before. Okay, which is kind of nice. Once you learn how to go one way, then you learn how to do it the opposite way. Okay, let's try another one. What about 2x cubed? Every time I put one on the board on here, I say on the board, but on the screen, go ahead and pause the video, try it on your own, and then come back and see if you get the same thing that I get. Okay, so when I see this, I think of this as 2 times the integral of x cubed dx. Well, that's just going to be 2 times x to the 4th over 4 plus c. I can reduce that, and I get x to the 4th over 2 plus c. You can do it that way. You actually don't have to do it that way. If you would like, you can leave the 2 on the inside and then just go straight into this step right here. The antiderivative of x cubed is x to the 4th over 4 plus c. You have x to the 4th over 2 plus c. Either way is perfectly fine. They give you the exact same thing. Now, one thing that I feel like some of us are probably confused about is why did I put just the parentheses around this and not the plus c? Okay, so technically speaking, I could do that. I could go ahead and do this right here. Okay, here's the catch with the c. I have no idea what the value of it is. So if I multiply c by 2, well, now it's just 2c. And I don't want to write 2c because it's still some arbitrary constant that I don't know its value. I'm just putting it there as a placeholder in the event that I had more information that I could actually solve for it. So because I don't know what it is, and I'm not going to know what it is without further information, I could, if I wanted to, put the parentheses here. But my final answer, I need to make sure that it's just plus c by itself all over here. Okay? Let's try another one. So the antiderivative of 1/2 x squared minus 4x to the 6th. Okay, so I'm going to do this one as 1/2. The antiderivative of just x squared is x cubed over 3 minus 4 times the antiderivative of x to the 6th is x to the 7th over 7, and then plus c. So clean this up a little bit. You have x to the 3rd over 6 minus 4x to the 7th over 7 plus c. That is the antiderivative of this function. Okay, we've got one more. Let's see. Ooh, this is written in a weird format. I could rewrite this. X to the negative 3 dx. Well, now if it's written in this format, okay, I can still use my reverse power rule. So x to the negative 3 plus 1, so negative 2 over negative 2 plus c. You are allowed to leave your answer just like that, or if you wanted to, you could write this as negative 1 over 2x squared plus c. Either one of these answers is perfectly fine. I will take either one. I don't have a set rule as to which one you have to follow. Okay? All right, what about this one? I have the square root of x here. Again, I want you to, every time I put a new one on the board or on the screen, pause it, try it on your own, come back, see if you get the same thing. So I've got square root of x. I'm going to rewrite this one as x to the 1/2 dx, just like we did when we were taking the derivative. Okay, sometimes when you take the antiderivative, it's helpful to rewrite it as a rational exponent. So then if I add 1, 1/2 plus 1 is going to be 3/2 over 3/2 plus c. That's kind of messy. So take the fraction, flip it, and multiply it up. So 2x to the 3/2 over 3 plus c. Make sense? All right, x times x plus 1. Ruh-roh. I haven't done any of those when they are multiplied. Oh, and that properties of integrals worksheet we did a while ago said that we weren't allowed to multiply. What do? Well, what if I wrote it like this? And just said x squared plus x. Well, now it's just an addition property. I'm allowed to do that. Yay! We're safe. So now I can just make this x cubed over 3 plus x squared over 2 plus c. Easy peasy. Okay, keep on going. Uh-oh. I had a feeling that was probably going to... that is what I wanted to do. Okay, so 2 sine... Oh my gosh, it's a trig function. It's okay. We got this. The 2 is going to stick around. Okay, something... Sine is the derivative of something. Sine is the derivative of something. Question is, what is that something? Well, nothing. Negative sine is the derivative of cosine. Ooh, okay. So that must mean if I took the derivative of negative cosine, then I would get sine. Well, let's check. So negative 2 cosine of x plus c. So you've got, if you took the derivative of this, dx of negative 2 cosine x. So then, I mean, you can have that plus c in there. It's just the constant. It's going to be 0 anyway. So the negative 2 sticks around. The derivative of cosine is negative sine. So negative times negative, there we go, becomes positive. So we are A-okay there. So the antiderivative of sine is negative cosine. That might come in handy for you to memorize in the future. Maybe, maybe not. I don't know. Secant squared, another trig one. Oh my! Well, secant squared, that seems pretty common. I think we've talked about that before. Wait a minute. The derivative of something is secant squared. Question is, what is that something? I know what the something is. That something is the tangent of x plus c. So remember how we were able to take the derivative? Now you're going to be able to go the opposite direction and take the antiderivative. How cool is that? So cool. So cool. But what if you could actually figure out what c is? Well, how do I do that? Hopefully I have some information here. There should be like, there it is. I was looking for that. Okay. Find the general solution of that and the particular solution that satisfies the initial condition f of 1 equals 0. All right, I'm hearing heads rolling right now. Like, what? What? Okay, so basically, if I want to find the general solution of something, that's code word for take the antiderivative, okay? So my antiderivative is the integral of this guy. Okay, so let's start with that. So I've got x to the negative 2 dx. I take the antiderivative, and I'm going to have x to the negative 1 over negative 1 plus c. So f of x is equal to negative 1 over x plus c. This is my general solution because I don't know what c is. C represents some constant that I need to figure out what it is. To find out what that is, I use something called an initial condition. Okay? I have the initial condition that when I plug in a 1 for x into this guy right here, I'm supposed to get a 0 overall. So if f of 1 equals 0, so then I've got f of x is equal to negative 1 over x plus c. So I'm going to plug in 1 here and 1 here. So f of 1 is equal to negative 1 over 1 plus c, which I already know that f of 1 is supposed to be 0. is negative 1 plus c, so c must equal positive 1. So now my particular solution is f of x is equal to negative 1 over x plus 1. But this is only true when f of 1 equals 0. This would be completely different if I had a different particular, if I had a different initial condition. So you have a different particular solution. Okay. So I hope that helps explain how to do antiderivatives. You're going to do a lot of practice with this because it is going to take us a little while to kind of get the hang of this. As always, Prof. Rob Bob, Khan Academy, and oh, what's the other one? Oh, yeah, that's right, your textbook. Use any of those resources at your disposal, and they will help you out.